about the experimental outcome, sample space, and sample point. If you have any question,
No,
because yes,
clear.
clear. Okay. So let me put as experiment. No, it's definitions that we have already. Experiment is any process that generates well-defined outcomes. The sample space of an experiment is the set of all experimental outcomes. For example, coin toss is your experiment, and experimental outcomes are head and tail. An experimental outcome is also called the sample point. So head is also sample point, tail is also a sample point. So these are the examples: tossing a coin, selecting a part for inspection, playing a ball game, conducting a sale. So these are the experiments and these are the experimental outcomes. So I will be more fast in this lecture because we have covered the basic things. Now we are trying to discuss the counting rule. So could you tell me why the counting rule is so important? Because you have already a good background in statistics. So could you tell me why, in terms of probability, the counting rule is important? You have any idea? Experiment, because counting rule is important, because counting rule will provide you the total number of experimental outcomes, total number of experimental outcomes will be provided by the counting rule if your experiment involves steps in it. For example, let me go to the okay. So why, I mean, the counting rule is important because it will give us total number of experimental outcomes. So let me move on to the our for example, you have one coin, uh, maybe coin one. Coin one has two experimental outcomes, head and tail.
Okay.
Okay, and we have another coin, second coin, and it will have again head and tail. So for the coin one, if we gonna toss, we may have head and tail, or if we're tossing a second coin, mean the second time we toss, we can have the head and tail. Okay, so if the two coins involved in the experiment, if two coins involved, then what will happen to the sample space? Because for the single sample space, for the single coin toss is head and tail, we already know that. But when the two coins involved, so what will happen to the sample space? So I'm just gonna use a tree diagram in order to make you understand, I mean, why the counting rule is important. So let me move it high. For example, you have the first coin and you have head and tail. Okay. After the first coin, you will have second coin. For example, from the first coin, if you have head, and for the second coin, if you have head, you will again have head, head, and head, tail. For example, if the first coin is head, the second will also be head. If the first coin is head, the second will be tail. But if the first coin is tail, the second coin can be head, and if the first coin is tail, the second coin can also be tail. So this is the first experimental outcome. It is kind of, this is 1, 2, 3, and 4. How many experimental outcomes are there?
4.
4. So it means that when there are multiple coins involved, then the experimental outcome, or you can say the sample space, will increase. Okay, so this is the multiplication rule that will help us to determine the total number of sample points. For example, in the first coin toss, you was having 2 experimental outcome. Multiply by, for the second coin toss, you have 2 experimental outcome. So 2 multiplied by 2, answer is 4. So this is the demonstration practically. I have shown you the practically how mean the 4 experimental outcomes we have obtained. And this is the simple multiplication rule that will guide us how to calculate the total number of sample points, or you can say the total number of experimental outcomes, or you can say the sample space for the 2 coin toss. Okay, so for example, there is a situation that you're gonna have in the first step, you have coin toss. It means there are 2 experimental outcomes. In the second step, you have to roll a dice. It means how many experimental outcomes are there in the dice case? 6. Is it true?
Yes.
So 2 multiplied by 6 equal to 12.
12.
So your total number of sample points are 12. So in that case, we haven't make any tree diagram, but through the multiplication rule, we can determine the total number of sample points, because this is very crucial for calculating the probability, because it is your main denominator. Because when you are calculating the probability of any event A, then your event of interest may be it's NA over N. So your N is basically, your denominator is this total number of sample points, this N. So this is the main denominator in any probability case. That's why it is very important to determine the total number of experimental outcome, because it is your main denominator when you are calculating the probabilities. Okay, so for example, if you are interested in calculating the probability of having simultaneously 2 heads, for example, if you're going to bet with someone that I'm going to have two heads, one after another. So it means that you are interested in calculating the probability of one head and second head. So in that case, the probability will be, what will be the probability? Could you tell me?
1/4.
1/4. Very good. So this is gonna be the probability in case of two heads. Now I will show you how we have reached to this conclusion, because you can see your sample space here. Two head, head tail, tail head, and two tails. So this is the only event out of four, because these are 1, 2, 3, 4 events, and two heads is only the one event out of four. So that's why we can write here two head mean the one event only, and divided by the four mean total number of experimental outcome. So that's why it's really important to know about the total number of experimental outcomes. If you have any question during my discussion, my explanation, you can ask me, you can interrupt me anytime. Okay, and further I'm gonna show you some examples, maybe some explanation, so you will now easily understand what is the meaning of the multiple step experiment. If an experiment consists of a sequence of case steps in which there are n possible results for first step and two possible results for the second step, and so on, then the total number of experimental outcome is given by n1 multiplied by n2, and so on. So n1 is your experimental outcome at step 1, n2 is your experimental outcome at step 2, and so on. So you're going to multiply these, and you're going to have your total number of experimental outcome. A helpful graphical representation of multiple step experiment is tree diagram. So I have also shown you this tree diagram. Okay. So this is the example. I think I have already explained this example. Total number of experimental outcome is 2 multiplied by 2 is equal to 4, and we have already seen how we have achieved this result. So there is another example. Let's another example. Kentucky Power Light Company starting an expansion project. The project consists of two stages, design and construction. So there are two stages, design and construction. Design work can be completed in 2, 3, or 4 months. Construction work can be completed in 6, 7, or 8 months. So you can see that in the design we have basically two steps: design there are two steps. One is design, another is construction. Okay, there are two, design and construction. So design part has 1, 2, 3. Design part has 3 experimental outcomes, so we can write here 3. And construction part also has 3 experimental outcome, I mean 6, 7, 8. In total, these are 3 experimental outcome. So we can write 3 as well here. So total number of 9 experimental outcome in this case. Okay. So this is the experimental outcome, total number of experimental outcome in case of this problem. Okay. And now we are moving to the combination. So I think let me have some. Please wait a minute. My son is maybe there, and
Hello, Mr.
Yes, yes, yes.
I am with internet and now I enjoy in the class.
I'm just yes,
My name
yes.
is Radari.
Okay,
No,
okay.
okay.
I'm gonna put you present. No problem. Please wait a
Okay.
minute. I'm just gonna deal with my son because he's there. Yes. Sorry for inconvenience. Uh, my kid was here.
No problem, Mister.
Okay, so now we are moving to combination, and there is another permutation. So these are also techniques used uh, for driving the in order to have your total number of experimental outcomes. Combination and permutation. Do you have any idea about permutation and combinations? Any idea about permutation and combination? Any one of you? Let me put Atari present. If you have any idea, please let me know so that I'll try to explain you. Combinations
Yes,
and permutations.
we have study combination rule that to select, for example, 5 from a 20 student.
Mm-hmm. And permutation?
I don't know.
Okay. No problem. No problem. I will let you know. Basically, these are also the techniques for calculating the total number of experiment for certain situations. For certain situation, because these two techniques calculate the total number of arrangements. Arrangements or experimental outcome is the same thing. Is the same thing. Total number of possible arrangements. Both combination and permutation. So the objective of combination and objective of the permutation is to give the total number of possible arrangements. These total number of possible arrangements can also be called the experimental outcomes, or you can say the sample space. Now, the problem comes next. So, in if combination and permutation gives the total number of possible arrangements, then in what situation, what will be the situation for combination, and what will be the situation for permutation? What is the meaning of situation here in case of combination and permutation? So please note that for the combination, the position doesn't matter. The position doesn't have any significance. Okay, if any situation, for example, I'm going to give you a situation. For example, there are maybe 20 peoples, 20 people in the students, maybe 20 students are there, and we have to select 5 students for maybe any sort of you can say the maybe class representation, CR. We have to select 5 CRs out of 20 students. We have to select 5 CRs. It means that among the 5 CRs, each you have to select CR1 and until CR5. So the first position is also CR, second position is also CR, and so on. The 5th position is also CR. All are CRs. It means that in this situation, position doesn't matter. Does not matter. Position does not matter. When all the students that you are choosing are going to be the CR, it means that the position is the same for all students. Position doesn't matter. So in that case, if we wanted to calculate the total number of arrangements, then we will apply the combination formula 20C5. Okay, but for example, if we are going to select, for example, we have 20 students there again, and we have to select maybe 3 students for their ranking. Maybe the first, in terms of their marks, maybe the first, the second, or maybe the third. Okay, or you can say best, average, or worst. So in this situation, you see that first position is not similar with the second position. The second is not similar with the third position. So the all positions are different. We are selecting out of 23 students, but the position here matters. Positions matter. So position is important. Okay, so in those situations where the position is important, so we apply the permutation. We can calculate the total number of experimental outcomes or total number of arrangement through the permutation formula, because both of these formula give us the total number of arrangements, but we have to apply these two formulas very carefully by considering our situation. If in our situation, if the ranking is not important, it means that you can apply the combination formula. If the ranking is important, then you have to apply the permutation formula. Permutation, some people say permutations, combination. So did you get that point? If you are okay, then we can move on.
Mister,
Yes.
sorry for being late. I have internet issues.
Okay. Let me, Saliha, let me put you Okay,
Sir, I'm
I have
also
put,
here.
okay, you are present as well.
Okay, thank you.
Okay. So I think all the Jamila is here. Jamila is here or not? I think she's not here, so she will remain absent. I'm gonna save it. Okay. So did you get the idea of permutation and combination?
Yes, sir.
Okay, so we'll move on. The basic objective of these formulas is to calculate the total number of experimental outcomes. These are the formulas for the combination. You see here n factorial. N is your total number of object, and n is your selection. So n factorial, n minus n factorial, and the same is here. I know very well that the online study is a great challenge, because in face-to-face classes the student can interact with students, and he can assess maybe from the faces as well. I mean, the teacher has ability to read the faces as well, and by identifying the faces he can tell whether the student is getting or not. So but I will try my best online, even if it is online, but I will try my best, so don't worry about that. So some of the examples are here. A home builder offers 4 different floor plans. Example, let me put in that way. So a home builder offers 4 different floor plans, 3 different exterior designs, and 2 types of roofs. How many ways can a home buyer choose his her home? So you see here 4 different floor plans here, because there are 4 experimental outcome is there. 3 for the different exterior design and 2 for the roof. So this is the example of multi-step formula. So there is another example for the combination. How many ways can a 3 Republicans be chosen as a member of committee from a group of 7 Republicans? So you see here, we have to select only 3 members, and in between the members there is no ranking involved. All 3 members are of equal rank. So that's why there is no any kind of ranking or ordering is there. So in the similar example regarding the permutation, automobile license plates in a state consist of 7 letters of the alphabets. A letter may not be repeated. How many license plates are possible? So you can see here 26, 26/7, because you have to choose 7 letters. You have to choose 7 letter, and there are total number of 26 letters. In English alphabets we have total 26 letters, and you have to select 7. And you see here why the order is important here. For example, if your car number is, for example, if your car number is 1, 2, 3, so maybe can you write instead of this 3, 2, 1? Will it be justified if you are writing your car number plate? For example, if the police has given you this number 1, 2, 3 is your registration number, and you're gonna put 3, 2, 1, is it justified in case of this?
No, Mr.
No, it is not justified because you have a unique combination. 1, 2, 3 is unique, and 3 to 1 is a unique number plate. These are both different. In case of permutation, these are different. In case of combination, this is the same. Okay, if you're considering a combination kind of stuff, these two cases are same. But if we are considering a case for the permutation, then these two, 1 to 3 and 3 to 1, these are different. Especially for example, when you have to generate your PIN code for your credit card, these are also example of permutation because everyone has his own maybe PIN code, maybe 1, 2, 3, 4 and 4, 3, 2, 1 is different. Okay, you cannot maybe use in different arrangements when you have to use in case of PIN code, maybe your also same kind of passwords. Password is also example of permutation because every password is unique thing. I hope you are getting it.
Yes.
Automobile, for example, what is the example? Is there any example in case of combination in your mind? Could you tell me any example? I'm going to give you one interesting example. For example, you have maybe 5 fruits: apple, banana, maybe apple, banana, strawberry, or maybe some sort of, what fruit do you like?
Orange.
Maybe orange. So these are 5 fruits. So in case of these, total number of fruits are 5, and we have to select any maybe 2 fruits out of these. So for example, if we're selecting apple, and we first select apple and then we select banana, and then we put in the machine. And there will be any kind of mixture. So you're gonna have apple banana juice. So for example, you are going to take banana first and then apple after that, and again you put in the machine. So will these juices will be different or the same?
Same.
Same. So this is the example of combination. So this is the example of combination because in this situation, order doesn't matter. Because if you put apple and then banana, no problem. Or you put banana first and then apple, no problem. So, but in case of password, in case of PIN code, you can't change your order because order is very, very important. So when order is important, then you have to apply permutation. When order is not important, then you have to apply the combination. So I think you can, these are just examples. You can read it. We can move on. So I think these concept we have discussed in last lecture: classical method, relative frequency method, subjective method, and you can just see the example of classical method. And I think in last class we have also discussed the dice throw, rolling a die problem, where the sample space points are 6, and if you wanted to calculate the probability in by using the classical method, then you have to calculate the total number of experimental outcomes. So in the dice throw, the total number of experimental outcomes are 6. So probability of each experimental outcome or each sample point is 1 out of 6. So you can and this is the relative frequency approach. I think in the last lecture the similar type of table was there, and you can maybe check if you have any sort of problem, then you can ask me. But it's a simple thing. I think you can easily, for example, you can calculate the probability of each experimental outcome in the relative frequency method. The 0, 1, 2, 3, 4, these are all experimental outcomes. And how you gonna calculate the probability? You have to calculate, you can calculate your probability by having your event of interest divided by the total number of experimental points. For example, if you would like to calculate the probability of 1, for example, probability that a patient, only one patient is waiting, probability that only one patient is waiting, the probability gonna be 5 out of 20, because 5 is corresponding to 1 and 20 is the total number of experimental outcomes. So for example, if you wanted to calculate the probability of 3 patients are waiting, its probability will be 4 out of 20. Okay, it's very simple one. So these are few examples. You can look by yourself. The probability of 0 patient waiting for service is 2 by 20. You can see it's 2 by total is 20. The simple relative frequency approach. And subjective one, I have I think in the last lecture we have discussed this subjective approach because it's related to your degree of belief. Okay, your knowledge, your experience will guide you through some situation, and you can predict some maybe future situation. Maybe you can say it's your sixth sense. Events and their probabilities. So event is really important concept, and in the last lecture I didn't have this tab, but today I have this tab, and I can show you in how we can have the events out of the experimental outcomes. So it's a very simple concept. Don't be I think don't shy to ask me any question. If you have any question, just ask me. Okay. So now I'm going to talk about the event. For example, we have sample space, head and tail. Okay. So you know that the null set is the subset of every set. Null set is the subset of every set. We have written the experimental outcomes in the form of set. So this is the form of set. So now we are trying to make the subsets. Head is also the subset of this set. Tail is also the subset of this set. And set itself is also the subset of each set. So how many subsets are there? 1, 2, 3, 4. So these are 4 subsets are available if your experimental outcome, if your sample space have 2 points, then how many experimental outcomes are here? Sorry, how many subsets are here? The subsets are 4. In case of when your sample space has 2 points, head and tail, in that case, your subsets are 4. So we can say these subsets as events. So this is the only case for when your experimental outcome has 2 sample points. So null set is the event, head is the event, tail is the event, head and tail is the event. Now the next thing is to apply the knowledge of probability to calculate the probability of each event. For example, if you wanted to calculate the probability of null set, what is the meaning of this one? If you wanted to calculate the probability of null, what is the meaning in this situation of coin toss? Because we have situation of coin toss. What is the meaning of how do we calculate the probability of null set or or the event, the first event? Do you know? First of all, we need to understand the meaning of null. First of all, we need to understand the meaning of null. The meaning of null is that it's very important. Please be careful. It's very important. The null is that when you toss a coin, no, nothing will be there. Nothing. Sorry. You know, using a tablet is also a challenge. When you toss a coin, nothing will be there. Nothing will be there. So now I'm gonna ask you a question. Please answer me. When you going, for example, I have given you a coin. And you are going to toss. Is it possible that nothing will be there? Is it? I have given you a coin. Is it possible that nothing will be there after tossing? Is it possible that nothing will be there when you are going to toss a coin? When you are going to toss a coin, it means that something will be there. It could be head, it could be tail. It means that the probability that nothing will be there, the chances are 0. You got my point?
0.
Yes, 0. Nothing will be there, the chances is 0. Because something will be there. Because you are going to toss a coin. So something will be there. It is not possible that nothing will be there. It means that if nothing will be there, the chance is 0. You got my point?
Yes, Mr.
So in this situation, I have just calculated the probability of this first event. Now I am moving on the second event. The second event is head. What is the probability of head? It's very simple. 1/2. What is the probability of tail?
1/2.
1/2. No, the fourth event is very, very crucial. The fourth event is very, very crucial to understand, because probability of head was easy, probability of tail was easy to understand, but the fourth event is very crucial. because it's a combination of two, head and tail. Mean you have head and tail. So if we are treating this as event, so what mean, how do we calculate probability in case of this situation? In this situation,
Zero.
what we are going, no, what we are going to do, we are going to use addition method. We apply the probability of head plus we have to calculate the probability of tail, and then adding these two, we gonna get 1. So what is now the meaning of it? We mean, the main thing is to understand the meaning of this one. The meaning is this one, this event. So I am trying to explain you the meaning of this event. The head and tail, this is an event. The meaning of it is, if I am going to toss either head or tail will be there. Okay, for example, I have given you a coin and you're going to toss. It means that there is a probability that there is a for sure probability, mean for sure that they're gonna be head or tail. Is, am I right or not?
Yes.
When you are going to toss, it means that head or tail will be there. So it's 100% chance that head or tail will be there. So it means that you can see here the last event, we have calculated the probability 1. So it means that the probability of either head or tail is 100%. Okay, so this is basically I was trying to explain you about the events, mean how do we generate the events and how do we calculate the probability related to these events. So now we will see in more detail in the following slides. The probability of any event is equal to the sum of the probabilities of sample points in the event. This second line is very important, that I have tried you to explain here in this part. The second line, if you read the second line of the slides, the probability of any event is equal to the sum of the probabilities of sample points in the events. So in this event, we have two sample points, head and tail. So the probability is the sum of two sample points. The probability of head plus probability of tail, 1/2 plus 1/2 equal to 100. So that what actually the meaning of this statement that I have tried to explain in the there. If we can identify all sample points of an experiment and assign probability to each, we can compute the probability of an event. Okay, it's simple. So here is one example. We have a project in which design and construction is involved. Okay. At step 1, S1 means the step 1 involved design and the second step involves the construction. And completion time is given in months. For example, design is taking 2 months in first step. In the second step, construction takes 6 months. And then your sample point becomes 2,6. Okay. And then at step 1, design takes 2 months, construction 7, and so on. This is the basically explanation of this table, and these are the sample points. These are the sample points. Okay. So now I'm gonna move to the next part, and will let you know about the significance of event. I mean, how do we use events in real life problem? For example, in this problem, we want to find out probability of completing the expansion project in 10 months or less. So we are specifying that here that we just need only those projects which have completed in 10 months or less. So in this situation, we are going to our table. In our table, this is our table. So in that table, we can see that 2 month and 6 month, this is 8 month. So this can be a part of our event. 279, it can also be part of our event. 28, 2 plus 8 is 10. This can also be part of our event. 36, 3 plus 6, 9. So this can also be part of our event. And 37 is equal to 10. So this is also part of our event. So remaining 3 plus 8 is 11. So useless. 4 plus 10. Sorry, 4 plus 6 is 10. So this can be used. 4, 7, 11. So this is useless because we need only 10 or less. And 4 and 8 is also useless. So we have just come up with these events, these experimental outcomes, or you can say these sample points: 26, 27, 28, 23, 37, and 46. These are the experimental outcomes, or sample points are here. That is related to this event, 10 months or less. So what is the procedure of calculating the probability? What I told you earlier. That you have to have your events with you have to have your sample points with you, and then you will able to calculate your probability. For example, our event was 10 months or less. This is basically our event. So by considering this event, we have collected our points here, which is maybe 26, and let me 27, 28, 36, 36, 37, 37, 46. So these are the events. These are the sample points that is related to this event, because in any event the multiple sample points can be involved. So if the multiple sample points involved, so for example, I am giving this event any name. For example, I can give this event a name C. So if I am interested in finding the probability of C, it means that probability of this plus probability of this, probability of this, plus probability of this one, and plus the probability of this one, plus the probability of this one. So I'm gonna add all the probabilities related to these sample points if I'm interested in calculating the probability to related to this specific event. Okay. So how do we calculate the probability? How do we calculate the probability? Do you know? What is important if we wanted to calculate the probability? What is important is the total outcomes, total experimental outcomes. So in this situation, for example, in this situation, how many experimental outcomes are here? Sorry, sample points 1, 2, 3, 4, 5, 6, 7, 8, 9. So these are 9 sample points. Okay. So when you are calculating the probability of this one, it means it is 1 out of 9. Cos 2, 6, only one event out of 9, plus 2, 7 is one event out of 9, and so on. So in that case, you can calculate the probability of this event. Did you get this point? Got it?
Yes.
Okay. So the slides is also is here. You can visit the slides as well. No, this is the simple one. The New York is 54, California 52, Texas 48, Illinois 33, Ohio 30. Find the probability of n. For example, New York is what could be the probability of New York? So we have to calculate, we have to add 54, 52, 48, 33, 30. We have to add all these numbers, and this will become our main denominator. And in that case, we can calculate the probability of n by 54 divided by the total. And in case of probability of B, sorry, the text, I don't know the B here, maybe some error here. The probability of Texas is 48 out of total. Okay. Now, this is also a very important concept. This is called the complement of an event. Union of two events, intersection of two events, mutually exclusive events. Do you know the idea of complement? Do you know the idea of complement? Complement. Any idea about the complement? For example, during the COVID, there was vaccine. Which vaccine have you taken? Pfizer?
Yes.
Moderna? Pfizer. Okay. So do you know the effectivity, or maybe the effectivity of Pfizer mean in terms of percentage? How much is the Pfizer effectiveness of Pfizer vaccine? So let's say it's because I was reading, I was just maybe Google the numbers about the different vaccine, and maybe the Chinese vaccine were effective by 50%. And I think Pfizer was, these are Chinese. and maybe the Pfizer, because it was American, so it was, I think, 80% effective. So if a vaccine is 80% effective, so what is the percentage for ineffectiveness? Ineffectiveness. If the vaccine is effective by 80%, so what is the percentage for ineffectiveness? Do you know? If the vaccine is effective by 80%, so what is the, if the vaccine is not effective, mean not effective, you can say 20%. Okay. So this is, for example, if your objective is to calculate the probability of effective, for example, you can write the probability of the effectiveness is 80%, or you can write 0.08. And if you wanted to calculate the probability of ineffectiveness, so mathematically I'm going to write here by complement e raised to power c, and we can write probability of e, 1 minus probability of e. So now 1 minus probability of e, and probability of e is 80%. So your answer is 20%. Did you get my point?
Yes, Mr.
So this is event and this is the complement. So here is the explanation. This is the event and this is the complement, and complement is basically the reverse probability, reverse. And how do we calculate the reverse? Just 1 minus the this one, the original one. 80%, the reverse of 80% is 20%. The reverse of 20% is 80%. So you can write, according to your problem, if someone has given you the probability of anything, for example, probability of defective of any defective item is 5%. I think there is maybe problem in camera, but the lecture is going on, no problem. If the probability of a defective item is, sorry, is 5%, and we can write 5% as 0.05. So what is the probability of this one? Not defective. So this is for defective, and D complement is for not defective. So what is the probability? 1 minus probability of D, which is 1 minus 0.05. Answer is 95%. Okay. So did you get the idea of complement?
Yes, Mr.
Okay. So now
Yes,
we are moving to the idea of unions. I think union is simple, and let me move on. So by the Venn diagram, you can easily understand this area is event A, in the circle is event A, and the rest area is A complement other than A. Complement is basically the area other than A. So now I think probability of union A union B can be calculated, because the idea of union, I can remind you if you want. I can, for example, your A is 1, 2, 3, and your B is 4, 5, 6. So what is A union B? A union B is 1, 2, 3, 4, 5, 6. So this is A union B. So you can, for example, if there is any kind of common element, you just need to write only once. For example, we can have an element here. For example, 4. So it means that 1, 2, 3, 4, and this 4, 5, 6. So this 4, you may not write this 4, just 5, 6. So it's your complete A union B. The repetition is not allowed in A union B. Okay, you can write element from set A, you can write element from set B, but the repetition is not allowed. Okay, this is the idea of A union B, and in Venn diagram, it's basically from both these two sets. So later on, I will write in case of probability. The intersection is basically in the Venn diagram is the common area. For example, in our previous example, if we have seen here, this 4 is common. This 4 is common. So A intersection B is only 4, because we are just considering a common element. So the 4 is only the common element. So we are just considering 4. So it means that by the Venn diagram, we can write in the form of circle like this one. So in the circle, 4 is common, 1, 2, 3, 5, 6 is here. So the 4 is common. So this is the intersection part. Okay. So I think this is the simple one. And now we are moving to the addition law in term of probability. So addition law is basically probability of A plus probability of B minus probability of A intersection B. So I think this is very normal addition law, and you can just calculate the probability, because addition law gives you increase probabilities. Your probability increase when the addition is involved. When there's addition of two, when the addition of two events is involved, it means your probability will increase. For example, you have in the class you have some students from the maybe data science, and maybe some students from the maybe computer science, or maybe computer engineering. So my task is to select a student from the class. So I'm gonna write probability, that mean D for data science and C for computer engineering. So probability of D or C, mean my task is to select a student. So it means that if there are two types of student in the class, so I don't know to whom I'm gonna select. So I have to write this one, probability of D or C. Okay, probability of D or C, because I don't know to whom are going to select. So probability of D or C is equal to probability of D plus probability of C minus probability of D intersection C. So now I'm trying. Now I'm trying to explain you. For example, you have data science students are 10 and computer science students are 20. So what is the probability of D? What is the probability of D? Data science students?
10.
10.
10 over 30.
10 out of 30. Very good. And this one?
20
5
over
over
10.
30.
20 over 30. No, this is the most crucial. What about this one?
Don't give it.
This will be 0 because he is asking that he need this event require those students who have both data science and computer engineers both together. For example, if they are if some students in the class, for example, let's say we increase the class and there are maybe 10 students more, and these 10 students have both these 10 students both data science and computer engineer. These 10 students are very good and they are specialists in data science as well as in computer engineering. So these are more expert, these 10 students. So in that case, now we got this number. So if we got this number, so now the interesting situation will come here, and I'm gonna ask you the answer. So for example, what should I write if I have to rewrite here? So what should I write here? 10 by
10 over 40.
40, 20
20
out
over
of
40.
40 and minus
10 over 40.
40. So now you got my point, because this is the addition law in probability, and if the event are mutually exclusive, mean if the intersection of these two any two events is null set, basically, and if you don't have any information regarding this one, it means that this is going to be 0. But if they have provided you any information regarding the intersection, it means you will going to include. Otherwise, you have to understand from the experiment as well. From the experiment, you can understand by yourself. For example, in case of, I'm just a bit late, but I'm just going a very simple example. For example, in case of head or tail. So in case of head or tail, sorry, this is head plus tail. I'm not gonna write this one, head and tail, because when we are going to toss a coin, we don't have any kind of situation where both head and tail can appear at the same time. So this is impossible thing. So this is ultimately 0. You just 1 by 2 plus 1 by 2. Okay, so this is all for today, because we are maybe the time is already I think past. So if you have any type of question, just maybe I'm gonna share my WhatsApp number. Maybe you can just approach me or send me message through the WhatsApp, and we can have maybe team meeting accordingly, because this is not face to face. I'm not in Oman. You cannot access me in my office. Um, I think it is very important for student to approach the students if they have any problem. But in online cases, I think it's a bit difficult, but there is no any problem. You just give me a message. You can just me a message by sending an email or maybe some WhatsApp message, and then we can discuss the things. Okay, laterly, maybe after some time, I'm going to upload a weekly worksheet, and that will be very crucial for your exams as well. Okay.
Okay, Mr.
Have a nice time. So I'm gonna stop sharing the screen.